it do? All right, we'll come back to that. Does my acceleration change? I got a no from over here. Was there another no? A no from back there. I got two people who say no. Three, I think, if I interpreted Manal's head movement. Anyone else? Anyone want to say yes, the acceleration will change? I guess I should reword that. It's not a matter of whether you want to or not. Does anyone believe that the acceleration will change and wish to come out on record for that? Okay, then I guess the no's have it. Physics by democracy. Yeah, there's nothing in this equation that has anything to do with velocity here. So acceleration stays the same. So my acceleration is positive, my velocity is negative. What does that mean in terms of the motion of this object? Something we talked about in chapter 3. Pardon?
It might not move the object.
Oh, no, it's already moving to start with. Velocity is negative, acceleration is positive.
That means that it's slowing down.
Yes, it's slowing down. This thing starts out, basically picture this thing falling at 5 meters per second and someone's trying to keep it from hitting the ground. You're pushing up on it as this thing is falling. So my chart over here changes. So we start out at -5. How fast is it going after 1 second? Sorry, please don't mistake by doing this because you're wrong. I just did this because I didn't quite hear. No.
Negative 4.5.
-4.5. Because we're adding 0.5 every single time. This is positive.
Okay.
So -4.5. It's also slowing down. And then
Negative 4. Negative 3.5. Negative 3.
all right. So we now know what the velocity is. -3 meters per second. How far has it gone? Or what is the displacement of the mass?
Negative 4 meters. No. Negative 16.
Yes. How'd you get -16 meters?
Average velocity times 4 seconds.
The average is -4 meters per second. So on average, it's going -4 meters per second for 4 seconds, and so -16 meters. Questions here, but because I'm about to connect this with something else. All right. If the acceleration were 0. So picture an overhead view, this thing is sliding along this frictionless track at -5 meters per second. So if acceleration is 0 meters per second squared, how far does it travel? Now what displacement? What is the displacement? If the acceleration were 0, what would the displacement be? Assuming it still starts at -5. No, it's traveling at -5 meters per second. If acceleration is 0, what does that mean in terms of the velocity?
It's not changing.
Right. So if it's traveling -5 meters per second for 4 seconds, how far does it go? Or what's the displacement?
20 meters? 20 meters?
That would be how far, what is the displacement?
Negative 20 meters?
Yeah, -20 meters. So the displacement is -20 meters. If we had plugged into the formula the 1/2 GT squared, or sorry, 1/2 AT squared, again, this assumes initial velocity is 0, but it's not in this case. But this would be 1/2 times 0.5 times 8 squared, which is 4 meters. Notice that if I take the velocity, or take the displacement as if acceleration were 0, and then I take the displacement as if the initial velocity were 0, and I add them together, I get -16. That is not coincidence. That will always work. And I think I wrote this up on the board last time. I know there's either a PowerPoint or a video that's posted. Again, assuming acceleration is constant, here's the more general equation for displacement. If initial velocity is 0, we have that equation right there, which we talked about before. If acceleration is 0, we have that equation. Now, I know there's some students who look at that and that's just too many letters, and that's fine. We have other ways that we've already talked about solving these problems. But there are some students, I've done this before, there are some students who get on the test and they look at that and they remember it and use it. So it's for those of you for whom it will help. Okay. Any questions on this?
I'm sorry, how did you get the -16 meters for the displacement?
Originally based on the average velocity, the average of -4 and -3, or try that again, average of -5 and -3 is -4. So on average it's traveling -4 meters per second for 4 seconds,
Okay.
so you multiply. Or just plug into that equation. Other questions? Make sure this thing is still going. Yep. All right, so let's revisit something I think we did on the first day, or at least something I thought about on the first day. I have 2 objects here. This one has roughly twice the mass of this one. We'll assume it's close enough. The only difference would be the amount of ink inside, and I don't know if the ink really has significant amount of mass. So this has twice the mass of this one. It has twice the mass Therefore, it has twice the weight. This weighs 2 times what this does. If I drop them at the same time, which will hit the ground first, or the table first?
Same time.
At the same time. A couple other people nodding for it. Who? Same time, and Raphael? Everyone agrees. All right. And for those who just said same time, but didn't necessarily believe it, they indeed fall. Because you can always think about it in terms of these two that are falling as there's just two objects that are falling. There's no reason why they would fall at a different rate. Just because I connected like that doesn't mean that they're being pulled down any differently than they were before. Or from the equation that I wrote up earlier, or that's written right there too. If I double the mass, I'm doubling the force on it. So if I have twice the mass, I can have twice the force. Well, all I've done is just multiply both sides by 2. If I divide by 2, I'm back to what I started with. The acceleration stays the same. Or from this point of view, acceleration is force over mass. Here, acceleration is 2 times the force over 2 times the mass, which is just force over mass. So yet more support for the exact same thing, the fact that they would fall at the same rate. And so that all is done. Okay. Let's make a two-dimensional problem, and then we'll talk more specifics about friction. Let's make this a 7 kilogram mass. Push up with 3 newtons of force, and to the left with 4 newtons of force. Therefore, one of these right start. What is the acceleration? So how do we deal with a two-dimensional problem? What formula am I going to use to find acceleration?
The two forces divided by the mass.
Divide each one by the mass? Or
3 times 4 divided with 7.
3 times 4?
Yeah.
Ooh. How are forces added?
Would it be 3 plus 4 divided by 7?
We need to throw something else in there.
Equal acceleration.
Oh, no, not that.
The direction.
How do we take direction into account? If the 3 and the 4 were in the same direction, then yes, 3 plus 4. But they're not in the same direction. How do you deal with it?
Up is positive and left is positive.
All right, so, except if I just make them both positive, both directions positive, that's kind of confusing, because how do you differentiate between up and to the left?
Would the left be negative?
Whether the left is negative or positive doesn't change the problem, the issue that we're having right now. You could do that if you wanted to. Or you could make to the left positive, either way. But how do you deal with it when you've got 2 different directions and you can't get away with just a plus or minus to indicate direction anymore? This be day 1 or day 2 of the class.
Can you just find the resultant? Can you find the resultant?
That's one approach to take. So if we find the resultant, how do you add forces together? All right. So I'm going to the left 4 newtons. I go up 3 newtons. That whole head to tail thing, you know, like that lab that do in 2 days.
The
There was-
force will be 5. 5.
So that would be 5 newtons. We do have another issue here, but let's run with this for a second. So now, what is the acceleration?
5 divided 7.
So if I plug into F equals ma, I have 5 is equal to 7 times a, so a is 5/7. If this were a test problem, out of 10 points, you would get 4 points. All right, now you have 7 points. What is missing? What was the original question and compared to what we have right now?
Do you need the direction?
Yeah, direction is missing. Because originally I asked for the vector acceleration. This is the, if I just said what's the magnitude of the acceleration or what is the acceleration, the scalar acceleration, absolutely right, 10 out of 10. But I asked for the direction here. We have to somehow indicate a direction. Now, if you know trig, you could solve for this angle right here and come out, find the direction that way. But trig's not required for the course, so we have to have a simpler way of doing it, which goes back to how do we express the sum of these without using Pythagorean theorem? All right, somebody tell me the total force acting on it. Don't tell me 5 newtons. Tell me, based on the original problem, what's the total force? And make sure you include direction, because force is a vector. You don't have to get fancy, just talk about the forces.
Just like 3 newtons up and 4 newtons to the left?
So 3 newtons up and 4 newtons left. Okay. That works. It's, usually more writing than we like to do, but sure. That's the total force, that's equal to the mass times the acceleration. So how would you solve for acceleration?
Divide by 700.
Okay, so I have 3 newtons up plus 4 newtons left divided by 7 kilograms.
So would we put like the actual words up and left?
Hopefully not. If you did, it's not wrong, but there is a shorter way of doing it, which I'm slowly getting towards. Right. You about to tell me the shorter way, or you about to simplify this?
Well, you did mention saying I and J one time.
Yeah.
Yeah.
So over here, we could just write I hat. Don't forget the hat.
The hat.
And J hat. The unit vectors. The unit vectors keep us from having to write the word out. So this now becomes 3 newtons, I guess, was up, I hat, plus 4 newtons J hat over 7 kilograms. Let's bring it on home. How do we simplify this? How do we divide an addition problem by a single number?
Take 3 divided by 7. And it's gonna be, newtons I had, and then divide by kilograms.
So newtons I hat over kilograms. Traditionally, newtons per kilogram I hat is more traditional way of writing it. Are you stopping there?
And then plus 4 over 7 newtons over kilograms J.
You good with that? That's a very subtle nod there. It doesn't exude confidence. Are you good with this?
Yeah.
A little more confidence from over Manal. One more time, Taylor. Are you good with this?
Yes.
Okay. There are a couple other ways of expressing the exact same answer. 3/7 I hat plus 4/7 J hat. Put the whole thing in parentheses and then write your units out here. Don't forget the parentheses if you're doing it this way. Or you could also do, you could go decimal also, but 3/7 I hat plus 4/7 J hat. Meters per second squared also works. Now, traditionally, I hat's horizontal and J hat is vertical. For some reason, I flipped it. It doesn't matter because I defined it over there, so I don't have to go with tradition. And answer. You don't have to take it any farther than that. Some people are not satisfied with that. They feel like you have to have a number instead of a plus sign in there. The trouble is that if I did Pythagorean theorem at this point, I would end up with this, but you've now eliminated direction. And for those who wish to try their trig practice later, you could have also expressed this as 5/7 meters per second squared, comma, and then 153 degrees. Nope, try that again. 143 degrees.
Question. When you're using the resultant as the force, you don't put direction?
There is a direction here, and there should be a direction here. The trouble is that to get that direction requires trig.
Oh, okay, I see. That's why you put the degrees over there.
Yeah.
Like after you, if you did find out the direction.
Yeah, so I could have also expressed this, the force vector symbol, as 5 newtons, 143 degrees. Now the reason I know it's 143 degrees is that for a 3-4-5 triangle, this is a 37 degree angle, and that is a 53 degree angle. The 2 decimal, the 2 significant figures. And so 0 degrees this way, 90, 180. So when you express the angle like this, that's the angle right there. That's the 143 degrees. Some of that is beyond the scope of the course. It's just for the benefit of those who have done this stuff before and might find it simpler.
So like on a test, we could write it either way.
Right, yes. This is called rectangular form, and this is called polar form. All right. About to talk about friction. What causes friction? So, put the book on the table here, I push it, it stops. If Newton is to be believed, if there were no forces acting on that book, once I pushed it, it would go on forever. Which flashes back to the quiz of what force is required to keep something going, assuming it's going horizontally on a frictionless surface. Well, no force is required to keep it going. So since it did stop, since the velocity did change, there has to be some force acting on it, and we call that friction. So what can I do in order to increase the friction to make it stop sooner?
Use less force when pushing it?
That would cause it to stop sooner, would not change the amount of friction. So let me change the way I worded my question. What will affect the friction? Or assuming I push on it with the exact same amount of force, what would cause it to stop sooner?
The weight of it?
The weight of the book. Okay. So if I put this on top of the book, or that's not what you meant?
Yeah, I guess that's what I meant. So would that be the mass? Would that be considered the mass and not the weight?
Ooh. Why is it not the weight?
Because you're considering it as like how much mass it is instead of like the gravity pulling on it. Like the weight as in a force.
Mass is actually kilograms.
Yeah, mass is kilograms. The mass of the object does not directly affect the friction. But if I put this on the book, will it stop sooner, assuming I push on it with the exact same force?
Yes.
Anyone disagree? Anyone want to take the side bet? All right. Now, I don't know the exact force, but something like that. All right. So it did stop sooner. Did we change the weight of the book?
Yes. Oh, no.
Why not?
Same amount of force of weight would be active on it no matter how much its mass is.
Ooh.
Well, the book is still the same weight, you just added to it.
Oh.
You just added
Okay.
something else.
Right. The book hasn't changed. All of that is now something else. So what changed here between the book and the table? It wasn't the weight of the book.
Weight of the mass.
Ooh. Okay, the total, if I consider it the whole thing is one object, yeah, that has greater mass than just the book. But what changed between the book and the table?
Would it be there's a greater amount of friction on it?
Yes, there is a greater amount of friction, but right now if we assume that everything is level here, there's no friction acting on it. But what has changed?
The force?
I'm looking for something more specific. Think of this as,
Normal force?
there we go, box on ground.
Right.
The normal force between the book and the table has changed. The weight of the book has not, but the normal force between them is. We have these two surfaces that are now pressed more tightly together. So friction depends on normal force. and that is a sad marker. All right, so it depends on the normal force. Friction actually depends upon one other thing. So let's assume I've got this mass sitting on top of the book, and I want to make it easier to slide it. What could I do?
Add more force?
That might change how long it takes to stop if I change the amount of force, but it doesn't necessarily change the friction itself. I'm trying to think. Everyday life. What can be done to make one thing slide against something else more easily? Pardon?
Put something between them.
Something between it, that's, like grease it, like,
So what exactly does that do? If I put grease down, what does that do? Doesn't change the normal force. Normal force is still going to be the same. No, sorry, not the direction I was going in. I'm gonna spoil this one. Okay. Sorry. We'll do a long guessing game later on when we get to right before chapter 6. Something to look forward to. We're changing the surface itself. By adding a lubricant, we change the surface. I should actually, and I don't know if we'll be able to tell particularly easily, but we should have a different result if I did that too. Because here I've got this waxed cardboard against table, and here I've got this metal against the table. So friction depends upon the normal force and the surfaces, plural. Both surfaces. If you look up friction, what's going to be called the coefficient of friction, the tables will give you two surfaces because it does depend upon both surfaces. This will be encapsulated in something known as the coefficient of friction.